Representation Theory of Finite Groups, Lecture 4, Maschkes theorem. Let us start with some recap and the description of the setup. As usual, we work over the field of complex numbers, and G denotes a finite group. Let V be a finite dimensional G module. The module V is called simple, provided that it is non-zero and the only submodules of V are 0 and V. The module V is called semisimple, provided that it is a direct sum of simple modules. On the previous lecture, we learned the so-called Schur's lemma. So this lemma asserts the following. Every non-zero G homomorphism between simple G modules is an isomorphism. And the only endomorphisms of a simple G module are the scalar multiples of the identity map. So we also have seen the notion of multiplicity. Assume that we have a semi-simple G module V. Then we can write V as a direct sum of simple modules. And then we can collect together the simple summands which are isomorphic. So we can write V in the form Li to the power direct sum Ki, so which means that this is a direct sum of K1 copies of Li, plus L2 to the power direct sum K2, plus and so on, plus Lm to the power direct sum Km, where now all simple module Li's are pairwise non-isomorphic. And we have seen the uniqueness result, which says that this decomposition is unique up to isomorphism and permutation of summands. And the number Ki is called the multiplicity of the simple module Li in V. And if some simple module L does not appear in this decomposition, then we say that its multiplicity in V is 0. The usual notation for multiplicities is as follows. So it's either V over L or ML of V. So this is the multiplicity of a simple module L in a semisimple module V. And we have seen the interpretation of this number. So the multiplicity of the simple module L in a semisimple module V is equal to the dimension of the space of all G homomorphisms from L to V, and this is also equal to the dimension of the space of all G homomorphisms from V to L. So now we can formulate the main result of this lecture, which is known as Maschkes theorem. The statement is that every finite dimensional representation of a finite group over complex numbers is completely reducible. Or in module theoretic language, every finite dimensional G module over the complex numbers is semisimple. So the same result holds actually over any field of characteristic 0 or any field of sufficiently big positive characteristic. However, it fails in general over fields of small characteristic in the sense that the characteristic of the field divides the cardinality of the group G. And this is a very significant result. As we have discussed in the previous lecture, the fact that all G modules are semisimple reduces understanding of G modules to classification of simple G modules, because then any other module is obtained from simples by forming direct sums. So before we can prove Maschkes theorem, we need to recall inner product spaces. So let V be a finite dimensional complex vector space. An inner product on V is a function with two arguments from V and which has values in the field of complex numbers, which has the following properties. First of all, it is linear in the left variable, which means that it is additive in the left variable, and you can take out the scalars in the left variable. Then this function is symmetric up to complex conjugation. So V scalar product with W is equal to the complex conjugate of W scalar product with V. And finally, it is positive definite, which means that for any vector V, V scalar product with V is a non-negative real number, and it is 0 if and only if the original vector V was 0. So if we have a fixed inner product on some finite dimensional complex vector space V, we say that the pair V and this inner product is a Hermitian space. Here are some crucial for us properties of Hermitian spaces. So assume that we have a Hermitian space V with some fixed inner product on V. Let W be a subspace of V. The orthogonal complement to W is defined as the set of all vectors in V which are orthogonal to all vectors in W with respect to our inner product. The usual notation is W perpendicular as a right upper index. Here are the main properties for the notion of orthogonal complement. First of all, the only common vector for W and its orthogonal complement is the zero vector. Second, the whole space V is a direct sum of W and its orthogonal complement. And the third property is that the second orthogonal complement of W is equal to W. Remark, given some V, there are many ways to choose an inner product on V. Here is one standard way to choose inner product on the standard n-dimensional complex vector space Cn. So if you take vectors x1 and 2xn and take the scalar product with y1, y2, yn, let us define it as x1 times y1 complex conjugated plus x2 times y2 complex conjugated plus and so on. So this defines on the standard complex vector space the structure of a Hermitian space. Now let us discuss invariance of inner products with respect to the group action. Let V be a G module. Assume that we have some inner product on V. We will say that this inner product is G invariant, provided that for all elements V and W in V, and for any element G in G, the scalar product of V and W is equal to the scalar product of G of V and G of W. Example, if the action of G on V is trivial, which means that all elements of G act as the identity linear transformation of V, then, of course, any inner product on V is G invariant. Note that the condition that the scalar product of V and W is equal to the scalar product of G of V and G of W for all V, W, and G can be rewritten as a condition that the scalar product of G of V and W is equal to the scalar product of V and G inverse of W for all V, W, and G. So we can simply substitute W by G inverse of W and use that G of G inverse of W is equal to W. And this reformulation essentially says that if we have an invariant inner product, then for any element G in G, the linear operator given by G inverse is adjoint to the linear operator given by G. Next, let us discuss existence of invariant inner products. Proposition, let V be a G module. Then V has a G invariant inner product. Proof. Take some inner product on V. It exists. And define a new inner product, given by the round brackets, as the sum over all G in G, and then the old inner product applied to G of the first component and then G of the second component. So the claim is that this new inner product is an inner product and is G invariant. So let us check all axioms. First of all, the additivity of the new inner product with respect to the left variable. So if we take the inner product of V plus If we take the new inner product of V plus W and U, using the definition, we can write it as a sum over all G in G, and then the old inner product of G of V plus W and G of U. Using the additivity of the action of G, we can rewrite here the first variable as G of V plus G of W. And now using the additivity of the old inner product, we can split this into two summands, and then the first summand gives us exactly by definition the new inner product between v and u, and the second summand gives us by definition the new inner product between w and u. And this proves the additivity of the new inner product with respect to the left variable. And similarly, one checks that the new inner product is linear in the sense that you can move out scalars from the left variable. Next, let us check that the new inner product is actually symmetric up to complex conjugation. So take any two elements v and w in V, and let's write the new inner product of W and V. By definition, this is the sum over all G in G, old inner product of G of W and G of V. But the old inner product was an inner product, so if we swap G of W and G of V, we should put complex conjugate. By the additivity of complex conjugation, we can lift it over the sum. And then under the complex conjugation, we have exactly the new inner product of V and W. Similarly, we show that the new inner product is positive definite. For any element V in V, the new inner product of V with itself is a sum over all G in G, the old inner product of G of V and G of V. So here each summand is a non-negative real number, so the outcome is a non-negative real number. At the same time, this sum is zero if and only if each summand is zero, and each summand is zero if and only if V is zero. So this completes the proof that the new inner product is actually an inner product. Let us now check the G invariance of the new inner product. For any element H in G, let us try to compute the new inner product between H of V and H of W. By definition, this is equal to the sum over all G in G, the old inner product of G of H of V and G of H of W. Due to action axioms, we can write it as a sum over all G in G, the old inner product between GH of V and GH of W. However, since right multiplication with H is a bijective transformation from G to G, this can be written as a sum over all G in G, the old inner product between G of V and G of W. And this is finally equal to the new inner product between V and W. And this completes the proof of the proposition that any G module has a G-invariant inner product. Now we are ready to prove Maschke's theorem. We need to prove that any G module is semisimple. Let us do induction on the dimension of V. If the dimension of V is 1, then V is simple and hence semisimple. Let us now take V, some module of dimension which is greater than 1. If this module is simple, it is semisimple, and we are done. If it is not simple, it has a submodule W, which is different from 0 and V. Consider some G-invariant inner product on V, which exists because of the previous proposition, and let us look at the orthogonal complement W perpendicular. We claim that the orthogonal complement is a submodule of V. If we can prove this claim, then we know that the dimension of both W and its orthogonal complement is strictly smaller than the dimension of V. This is because the dimension of W is strictly smaller than the dimension of V and is strictly bigger than the dimension of 0. That is, it is strictly bigger than 0. Now, by induction, both W and W orthogonal complement are semisimple modules, and therefore V, being a direct sum of W and the orthogonal complement, is also a semisimple module. So what is left to prove is the claim that the orthogonal complement to a submodule is a submodule. So let us prove this claim. We want to prove that given any element V in the orthogonal complement to W and any G in G, G of V belongs to the orthogonal complement. In other words, we want G of V to be orthogonal to any element W in W. To check this, let us compute the scalar product between G of V and W. Using G invariance, we can rewrite it as a scalar product of V with G inverse of W. But W was a submodule, so G inverse of W belongs to W, while V was in the orthogonal complement. So this is equal to 0. And this completes the proof of both the claim and Maschkes theorem. Remark, the trick to introduce an invariant inner product is sometimes called the unitarization trick, because after we do this, each element of the group acts as a unitary linear operator. And also, if we look at Maschke's theorem and its proof, we have just proved that any submodule W of any G module V has a complement in V, namely W orthogonal complement is a complementary submodule. So V is isomorphic to the direct sum of W and its orthogonal complement. One consequence of this is that now we can prove that for any finite group G, there are at most the cardinality of G isomorphism classes of simple G modules. So the number of isomorphism classes of simple G modules is finite. Proof: let L be a simple G module. For a non-zero vector V in L, we know that there is a homomorphism from the regular module CG to L, sending the element G in G to G of V. This should be L. So this homomorphism is non-zero, and hence is surjective because L is simple. But the main thing is non-zero. However, by Maschke's theorem, the left regular module is semisimple. It's a G module, so it should be semisimple. So we can write it as a direct sum of pairwise non-isomorphic simple modules with some multiplicities. However, these multiplicities are exactly the dimensions of the Hom space. Since the dimension of the Hom space from CG to L is non-zero, the module L must be isomorphic to one of these Li's. But of course, the number m of such modules is at most the dimension of the regular module, which is equal to the cardinality of G. So here is an easy example. So let us decompose the regular Z3 module into a direct sum of simple modules. So Z3 is the additive group of residue classes modulo 3. So it consists of the classes of 0, 1, and 2. It's a cyclic group, it's generated by the element 1, and the matrix of adding 1 in the standard basis 0, 1, 2 of the left regular module over Z3 is as follows. So it's the matrix 0, 0, 1, 1, 0, 0, 0, 1, 0. The characteristic polynomial of this matrix is lambda cube minus 1. And if we denote by xi some primitive third root of unity, then the eigenvalues of this matrix are 1, xi, and xi squared. The eigenvector for 1 is 1, 1, 1. The eigenvector for xi is 1, xi squared, xi, and the eigenvector for xi squared is 1, xi, and xi squared. So now let us define U as the subspace generated by the eigenvector U, V the subspace generated by the eigenvector V, and W the subspace generated by the eigenvector W. So since our group is generated by 1, whatever is invariant under the action of the element 1 is also invariant under the action of the whole group. So since all subspaces are generated by eigenvectors for 1, they all are invariant under the action of 1. And hence they all are submodules. And they all are simple because they are one-dimensional. So these three submodules correspond to three eigenvectors which correspond to 3 different eigenvalues. And we know that eigenvectors which correspond to different eigenvalues must be linearly independent. So therefore, the regular module for Z3 decomposes as a direct sum of U, V, and W. So this is the decomposition of the regular module into a direct sum of simple modules. Note that in this case, U, V, and W are actually uniquely determined as submodules of the regular module. And this is because they all are non-isomorphic and the multiplicities are 1. Let us now look at a much more difficult example, the left regular representation of the symmetric group S3. So let us decompose this left regular module into a direct sum of simple modules. So the group S3 consists of 6 elements. So if we denote by S the transposition of 1 and 2, and by T the transposition of 2 and 3, then S3 consists of the identity of the element S, of the element T, the product ST, which is the cycle 1 goes to 2, goes to 3, back to 1. The element TS, which is a cycle 1 goes to 3, then it goes to 2, and then back to 1. And the element W0, which is a transposition of 1 and 3. And W0 is equal to STS and is also equal to TST. So in the basis given by the group elements, the matrices describing the action of S and T are as follows. So the left multiplication with S swaps E and S. So this is this part of the matrix. It swaps T and ST, this part, and it swaps TS and W0, this part. The left multiplication with T, it swaps E and T, the first and the third vector. So we have these ones. It swaps S and TS, so the vector 2 and the vector 5, and it also swaps ST and W0, so the vectors 4 and 6. So first of all, let us look at the sum of all elements in the group. And so we denote the sum by U, and let capital U be the subspace generated by this element. We already know that this is a submodule of the regular module, and it's isomorphic to the trivial representation of S3. So this module is of course simple because it has dimension 1. And it is very easy to see that the vector of coefficients 1, 1, 1, 1, 1, 1 is an eigenvector for both of our matrices with eigenvalue 1. So let us now look closer at eigenvectors for our matrices with different eigenvalues. So since both S and T are transpositions, they satisfy the equation that their square is equal to 1. So the only eigenvalues for these matrices are plus and minus 1. It is very easy to check that the linearly independent eigenvectors for S with eigenvalue 1 are 1, 1, all zeros, 0, 0, 1, 1, 0, 0, and 0, 0, 0, 0, 1, 1. And linearly independent eigenvectors for S with eigenvalue minus 1 are 1 minus 1, 4 zeros, 0, 0, 1 minus 1, 0, 0, and 0, 0, 0, 0, 1, minus 1. Similarly, linearly independent eigenvectors for T with eigenvalue 1 are 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 1. And linearly independent eigenvectors for T with eigenvalue minus 1, we just put minus sign into the second one in the 3 previous vectors. Okay, so now let us observe the following. The vector 1 minus 1 minus 1, 1, 1 minus 1 is a common eigenvector with eigenvalue minus 1 for both matrices S and T. So the corresponding element of the regular module is the element E minus S minus T plus ST plus TS minus W0. So you take the sum of group elements, but you add the sign depending on the sign of your element. Whether for odd elements, you write minus 1. So let V be the linear span of V. So we already know that V is an eigenvector for both S and T with eigenvalue minus 1. Since S and T generate S3, it follows that V is actually a submodule. So V is a one-dimensional S3 submodule. It is simple because it has dimension 1. And due to the signs appearing in the definition, this module V is usually called the sign S3 module. Consider the inner product on the left regular module for which the elements of the group form an orthonormal basis. Since G applied to an element in the group is an element in the group, and different elements in the group go under the multiplication with G to different elements in the group, in this inner product, each element of the group acts as a unitary operator. In particular, this inner product is actually S3, invariant. Now, let us compute the orthogonal complement to our eigenvector 1, 1, 1, 1, 1, 1, which we already used, inside the space of all S eigenvectors with eigenvalue 1. Then it is easy to see that the vector 1, 1, minus 1, minus 1, 0, 0, and the vector 1, 1, 0, 0, minus 1, minus 1, so they both are eigenvectors for S with eigenvalue 1. They are linearly independent, and they both are orthogonal to 1, 1, 1, 1, 1, 1. So since the total dimension of S eigenvectors with eigenvalue 1 is 3, so it follows that x1 and y1 form a basis in the orthogonal complement to 1, 1, 1, 1, 1, 1 inside the subspace of all S eigenvectors with eigenvalue 1. So let us take x1 and define x2 as the image of x1 under T. Let x be the linear span of x1 and x2. Similarly, take y1, define y2 as the image of y1 under T, and define capital Y as a linear span of y1 and y2. Claim both x and y are simple S3 submodules of the regular module. We prove the claim for x, and for y, the proof is very similar. We can explicitly compute that x2 is the vector minus 1, 0, 1, 0, 1, minus 1. So clearly, since x2 is tx1 and t squared is 0, then t times x2 gives us x1. Then we can compute that the action of S on x2 gives the vector 0, minus 1, 0, 1, minus 1, 1, and observe that this vector is exactly minus x1 minus x2. And this belongs to x. So x is actually stable under the action of both t and s. So it's a submodule. The eigenvectors for the matrix of T on X are x1 plus x2 and x1 minus x2. This one has eigenvalue 1 and this one has eigenvalue minus 1, of course up to scalars. The eigenvectors for S on X are x1 and x1 plus 2x2. Also, this one has eigenvalue 1 by definition and this one has eigenvalue minus 1. And again up to scalars. But in particular, there are no common eigenvectors, or there are no common non-zero eigenvectors. And the module X has dimension 2. If X were not simple, it would have a one-dimensional submodule, which would mean a common eigenvector for S and T. So X must be a simple S3 submodule. Similarly, Y is a simple S3 module. And directly from the construction, we see that the left regular module is a direct sum of u, v, x, and y. Finally, let us discuss multiplicities in the regular module. Let L be a simple G module. We have seen that for any VLL, there is a unique G homomorphism from the regular module to L, sending the identity to V. Consequently, the dimension of the space of G homomorphisms from the regular module to L is actually equal to the dimension of L. At the same time, the later is the multiplicity of L in CG. So each simple module has multiplicity equal to its dimension in the left regular module. So we can formulate it as follows. Let L1, L2, and so on, Lm be a complete and irredundant list of representatives of the isomorphism classes of simple G modules. Then the left regular representation C of G decomposes as a direct sum of L1 with multiplicity dimension of L1 plus L2 with multiplicity dimension of L2 plus and so on. So in particular, if you look at the last example, so this is the S3 example, U is a one-dimensional module, it has multiplicity 1. V is a one-dimensional module, it has multiplicity 1. And X and Y are two-dimensional modules, so they are isomorphic. So the corresponding simple two-dimensional module has multiplicity 2. Okay, let us finish with some problems and questions. Question 1. Prove with all details that the orthogonal complement is a subspace. Question 2. Construct an example of a G-invariant inner product on the left regular representation for any G. Question 3. Prove that for any M in G mod, the space of G homomorphisms from the left regular module to M is isomorphic to M by sending the homomorphism phi to the image of the identity element E under phi. Question 4. Decompose explicitly into a direct sum of simple modules the regular Z2 times Z2 module. Question 5. Let Z denote the linear subspace of the left regular S3 module spanned by the element Z1, which is the vector 2, 2, minus 1, minus 1, minus 1, minus 1, and the element Z2, which is the image of Z1 under T. Proves that Z is a simple S3 module isomorphic to X. So here we use the same notation as in our S3 example during the lecture. Thank you very much and see you next time.